Alright, so I thought I would work through, like I got all these guys painted here, all the way around. It's pretty much the first opportunity to use the full system. This hasn't existed until just now. So I thought I'd actually go through a sample of linear equations, a worksheet that I found online. So these are just random ass equations. Okay, so this one is 3y plus 8 equals 14. So on this side I'm only going to need 2. So this will be the 3y, this will be the 8, equals, I only need 14, so I only need one comparator, and I'm only going to need one of these guys over here. So I'm doing it the way I'm looking at it. This will be 3y plus 8 equals 14. So there's really only one variable, so we can just set it like that, and these two are going to be constants. So I've not always been as careful with that as I should. In the last video I messed up on that one. There was a constant that was marked as a variable. Anyway, you could have this be a variable and this be your constant. It doesn't really matter as long as you understand what you pick a meaning and you stick with it for the duration of the processing. Okay, so this is our y. I'm gonna have 3 of them. So 3y. This is 8, so that is this. Three y and 8 is 14. 14 is fun. So we're gonna go 27 minus 13. There we go. So there's our equation. 3y plus 8 equals 14. Now we want to consolidate our like terms. So these are our two constants. They have the same unit. So we want to bring them together on the same side of the equation. On the same side of the... There isn't even a word for this, I don't think, because if this was like this, you'd still do exactly the same thing. But it's not an equation anymore because that's an inequality. I'm not sure if there's a word for these in general, which annoys me. There probably is, but the fact that I don't know it, it's definitely not a widespread word. Anyway, so we want y on one side and all of our constants on the other side. So this constant needs to move over here. And in order to do that, we need to find its additive inverse and place it over here. That was hard. Virtue of balance ternary. You just flip the thing over as you cross the comparator, and your relationship remains unchanged. It's just as true as it was. Okay, so now we've got 14, and we're gonna, yeah, so that's a positive 14 and a negative 8. So what we're gonna have to do is, this is 27 minus 9 minus 9, that's just going to be 9. And then we're going to have this negative 3, nothing's happening there. And then these cancel off, so this is the value that we get. So both of these combined give us this. And we don't actually even need to know what that value is yet, because now what we're going to do is we want this to be 1y instead of 3y. Well, if we just rescale everything so that instead of this being our 1's unit, this is our 1's, right? Our 3 to the 0, 3 to the first. Well, now 1y is the same as 2. So y is 2. Because this would be 3 minus 1. Boom. There you go. So let's try another one. Let's maybe reset everything. You could just throw them back as they are, and we'll just deal with them later. Alright. I don't know how many I'm gonna need. I haven't chosen which equation I'm looking at. Let's see. Let's do... Okay. Let's do 1 equals 10 minus n. So we're gonna need a 1, and that's a constant. So that's on this side of the equation. And then I've got a 10, so that's a 9. Let's go the other way on that. Sometimes they bind up on each other. So that's a 9 plus a 1, so that's a 10. And then we've got over here, let's get everybody happy. We got our variable, but we want -1 of it. So we've got everything set, right? I have a positive 1, positive 10, and these are constants, so these are like terms, and a negative n, or x or y, or we can call it whatever the hell you want. Doesn't matter. That's one advantage to just using this abstraction for the variables. We're not committed to any particular name. No variable is called that, generally. So we get to use our imaginations. We're like, oh, well, this is whatever the fuck we want it to be. Okay. So, again, we want to consolidate our like terms. These are like terms. They're on opposite sides of our equation. This is the thing we're solving for. So if we take this guy, move it over with this guy, we'll isolate this, and we'll be able to figure out what this is supposed to be. So the way we do that, take this, flip it over. There you go. So now we've got a negative 9, or a negative, it's going to be negative 9 in a second, negative 10, and a positive 1, and these are commutative. We can swap these around however you want. All right. And if I were to bring this over here, we could swap these around. All right. Commutative property holds for all these guys. This is one of the virtues of this system. Okay. These ones annihilate. This one's real easy. I'm not going to need to grab a third one to do this one. These annihilate because they're opposites. Everything else on this one is a 0, so nothing else happens. So this just goes to 0. This goes away. Now, we could read this as negative 9 equals negative n, or x, or whatever the hell. But we could also just recognize these are the same polarity as each other. So, one of these is 9. There you go. We don't have to do any more manipulation. If you were writing it, and you have to track the negatives and the positives and the pluses and the minuses and all of this bullshit, you have to fix it. You have to, like, you'll have negative 9 equals negative 1n, or negative n, or whatever the hell. And you have to fix that and make it say 9 equals n. And then probably reverse it and say, well, n equals 9. And there's this nice trick, right? So, remember how I said before, if you're crossing this guy, you need to change the sign. Well, you only have to do that if we're crossing and leaving other things there. If we're just swapping sides, it doesn't matter, because that's the same as doing this. The equality doesn't care how I rotate it. This is why equality being symmetric, I've always thought this was a really weird property to even specify formally. Like, what the hell are you doing? Why are you mentioning this? Anyway, so we don't need it here. So yeah, that's the basics of how how to handle these guys. And you could even just leave these guys. You could use these as storage here. Just set everything to 0. Okay, this one has kind of a strange 0, but it's a 0 nonetheless. You could even just leave these guys here and just work your equation here, or with this one and this one, it doesn't matter. Yeah, still the same thing. And just get myself used to being strict about it. There we go. And now actually the way that I have this set, so I'm like kind of preferring to have a black up, black 0 up, with this very specific chirality on the unit nut, on the autumnal. Notice here I've got the way it rotates this way. I've got the constant first variable, second variable, but we can actually change that. If I take the nut and I flip it around, now it's constant first variable, second variable, going this way instead of this way. So we can actually leverage this. If you were to have, say, 2 on here, you could use that chirality to end up getting more options than you would normally. So the standard chirality that I'm using is this, where I have black facing up, red 0 this way, black 1 that way, first variable that way with the constant up. So the second variable is in line with the red, or if I flip it, the black, so the opposing color. And what this does is this tells me, the way that I've been doing it, that if I line up like this, if I have this kind of a 0, what that means, this is now pairing with that doubling, and that's indicating to me, that's the signal that I'm using to indicate repeating, right? So if this would be -1 repeating, and it would specifically be -1 repeating in as the polynomial expansion goes in the negative direction. We could have it the other way. So now it's actually repeating in both directions, or it's only repeating in the positive direction. So this ends up being quite powerful, taking note of how things are oriented. You can get, with just this very basic system, you can get all kinds of extra meaning on there that I haven't even mentioned or thought of yet. So yeah, there's a basic actual rundown, trying to be as careful as possible. I've probably fucked up in several ways, as is my wont. But yeah, that's a basic rundown of it. If I were doing division of something, so say I had like 9 divided by 4, the way I've been doing that would be to set it like this. So these guys, get these guys out of the way. So you might even like pull this over so that you have more room to represent this. So I've got this -9 divided by 4. That's going to be a really awkward thing to represent, particularly if you only have these 4 toton to work with. On this, you're definitely going to be able to do it, because the repeating the repeating terms on the polynomial are not going to be, I think there's going to be 2 of them. I could be wrong about that. Still not that familiar with balanced ternary, but yeah. So let's make it even more awkward. Let's do, say, like -9 on -5. So that would be 9/5. And you can tell because the largest term in the polynomial has the same polarity. So the whole thing has that same polarity. So this is just 9/5. So we don't have to worry about, is it -9 over -5? We don't have to worry about that because you can see it. It's just right there. If these are the same color, you're good. Like, the whole thing is going to be the, like, whatever polarity you want. It's positive, effectively. Like, the polarity that you're favoring, that's what positive generally is. Yeah, so I'll just represent it this way. And we could do even sums of things. So say we had, like, 9 plus x, all divided by 5. So let's represent it that way. Still figuring out how to use this space. In this case, we don't need that. Yeah, so I haven't quite figured out how to handle things like square roots or even exponents necessarily. But yeah, as it is, it's already significantly more powerful than just a basic, like, swan pond or something.